Go live. Come on. What's going on? I think it's actually... All right. So what we're going to do now, today, we're going to be focusing on our EIGRP. And we're going to have several different topics of EIGRP that we're going to be covering. We got some lecture, and then we also have, obviously, several discoveries that we're going to be going through. We're going to be spending a lot of time talking about EIGRP today in quite a bit of detail. All right? So let's get started with the lecture portion. Again, we're going to be in the ENARSI book today, not the Encore book. And you're going to jump ahead to section number 1, which is the implementing EIGRP section. All right? So EIGRP is a routing protocol. And the purpose of a dynamic routing protocol is to be able to allow us to exchange network reachability or network layer reachability information, meaning essentially destinations that are not directly connected to a router or not statically assigned to a router have to be dynamically learned in some fashion, okay? And EIGRP is one of those protocols that allows that to happen. All right? EIGRP was developed by Cisco as a proprietary protocol. It was one of the very first classless routing protocols that was developed back in the day. And originally it was Cisco proprietary. And then recently it became, well, not so recently now, it's been a while, but it became an open standard. At least some of the basic functionality of EIGRP became an open standard. Hold on one second. All right, became an open standard, and EIGRP released the ability for other vendors to implement EIGRP on their platforms. As its basic functionality anyway. But EIGRP is still under the control of Cisco. What we're going to be doing today is kind of looking at the implementation of EIGRP. We'll talk about the algorithm. We'll talk about the data structures that are going to be created by EIGRP as part of the process. There are 3 different data structures that get created with this protocol. A data structure essentially is a database that allows us to collect information and then decide what information we're going to use to make routing decisions. Those data structures include a neighbor table or adjacency table, which is a list of all the neighbors that EIGRP routers have. The second data structure is the topology table. A topology table is everything that EIGRP is learning through the EIGRP routing process, and then that's our EIGRP RIB. Remember we talked about that when we were in talking about Cisco Express forwarding, and then there is the EIGRP, or excuse me, the global routing table, the global routing information base, which are the EIGRP routes that get extracted from the topology table that end up going into our global routing table and being used in our global routing table. Okay, so EIGRP stands for the Enhanced Interior Gateway Routing Protocol. There are essentially, whenever you're learning about any sort of dynamic routing protocol, there are essentially three things that you need to understand about any dynamic routing protocol. All right. Number one, what is the algorithm that is used by the protocol? All right. And the algorithm is essentially defines how the protocol is going to function. Not only how it makes routing decisions, but how does it build its data structures? What kind of mechanisms does it have built in for redundancy and availability and failover? How is the metric used or calculated in order for us to be able to establish the best path that we're going to use in the route selection process and so on? So EIGRP happens to use something called the dual algorithm or diffuse update algorithm. OSPF, as an example, uses Dijkstra's algorithm, DIJK, RAS, Dijkstra's, yeah, which is the shortest path first algorithm. RIP uses the Bellman-Ford algorithm. BGP is a path selection protocol. So as such, it uses BGP path attributes. So it doesn't really necessarily have a specific algorithm that it uses, but it does have a path selection process that it uses, which we will see later on. So these are just some examples of some of the most common routing protocols and what algorithms they may use to make their decisions. So that's the number one thing that you need to know about a routing protocol. The second thing you need to know is what are the data structures that are created with the protocol. All right. And actually, with all these protocols, you're pretty much going to see the same basic data structures, with the exception of RIP, the routing information protocol. It's not quite the same. But what are the data structures that are created? And again, data structures are, in essence, the databases that are created that allows the protocol to operate and function, and allows the protocol to compile its information so we can take that compiled information and make a decision. So for example, in EIGRP, we have a adjacency table, what we call a neighbor table, which is a data structure that includes all of the relationships that EIGRP peers have with each other. These are our directly connected relationships. We have our topology table, like I mentioned before, which is essentially what we call the EIGRP rib. This is everything that EIGRP is learning. That is not a routing table. That is what EIGRP is learning from its peers, which could include, and also what it's advertising to its peers, which could include connected routes and other things. And then you have your global routing table, which is your standard rib or your standard routing information base. Now OSPF has very similar types of structures. In OSPF, we tend to call the neighbor table an adjacency database or adjacency table. We do have a topology table in OSPF. It's called the link state database. And then we also have the global rib. In RIP, we don't have a neighbor table because RIP routers don't actually officially form neighbor relationships. But they do have a topology table in RIP. And of course, we have our global routing table. In BGP, we have a neighbor table. We have a topology table. Show IPBGP will show us that topology table. And we have the global routing table as well. All right. Let's see. All right. Just checking in here. All right. Now, the last thing that you have to understand when it comes to, understanding dynamic routing protocols, it is part of the algorithm, but we kind of list this separately because each protocol has its own method for determining the best path or the path selection process, and that is the metric, or what I would define as the path selection process within the protocol. And EIGRP uses a complex metric, but in essence, there's a whole formula with k-values and calculations that are used for bandwidth, delay, reliability, and load. But in the end, it ends up essentially being bandwidth and delay are used to calculate the metric. OSPF uses a formula that is related to bandwidth. And again, it's a little bit more complex than just saying bandwidth. There's an actual calculation that's involved. RIP uses hop count, which is a really bad metric, and BGP uses path vector attributes, which are not metric values. So attributes, which is not a metric necessarily. They do have a value within BGP called the multi-exit discriminator, which is often referred to as a BGP metric, but it's just another attribute that BGP uses to be able to make a path selection. So you're going to find that BGP is kind of separate. All right, it's not really the same kind of protocol. Now, that being said, as we talk about EIGRP, and when we get into OSPF tomorrow as well, as we talk about these protocols, think about these three concepts throughout our entire discussion. All of our verification, all the functionality of the protocols, it's going to be tied around these elements. All right, of course, we'll look at Wireshark captures and I will, take a look at that. There is one other thing, so I will go ahead and make this 4 things, because this thing is kind of a secondary thing to the algorithm. The algorithm really defines the metric. The last thing are routing protocol messages. Now, keep in mind, these are dynamic protocols, meaning that they're actively sharing information with each other. So there are various routing protocol messages that are required in order for us to be able to share information. And one of the things that I like to discuss as part of the process is I like to discuss these messages. We'll take a look at what these messages look like in Wireshark. We'll break down the message format, what the purpose of the message is, and so on. But think of the routing protocol messages as the way information is shared between peers, right? And I'll even say, and verified. Verified. All right. So, for example, in EIGRP, we have hello packets. We have updates. We have replies. We have queries. Make sure I spell that right. Queries. There we go. And we have acknowledgments. All right. Hellos, updates, replies, queries, and acknowledgments. And each of these message types are used for a specific function of EIGRP. Each of these message types is used for a specific function. In OSPF, as an example, we use hellos. And we'll break down what each of these message types are used for. We have link state advertisements. I can't spell today. Advertisements. We have link state requests. And by the way, there are other message types. These are basically the message types, the most common message types that you're going to see. For example, in EIGRP, we have a stuck inactive query message type and so on. So there are other message types, but I'm kind of listing really the ones that are kind of critical for the function of EIGRP and OSPF and so on. We have database descriptors. I'll just put description. And we have link state acknowledgments. All right. And BGP, I'm not going to list them all, but we have open messages, we have notification messages, etc. There's going to be some other BGP messages that we'll talk about. So again, in order to understand, there's two aspects to dealing with every protocol. There's the aspect of configuration, which is a relatively simple thing to understand. Configuring these protocols is relatively simple. We saw that with spanning tree yesterday, right? There was a lot of theory. We spent hours talking about the spanning tree algorithm and all the different versions of spanning tree and so on. But when it came down to it, it was what, a couple of commands, 2 or 3 commands? It's kind of the same thing with these protocols. They're actually relatively easy to implement, but the whole point of CCNP is to be able to understand these details. What is a hello packet? If I'm troubleshooting the protocol, how can I identify that there's an issue with the protocol by looking at a hello capture, packet capture, or looking at a query or looking at a reply? Why does a query happen? What should I expect to... Did I spell query right? I don't know. That's a really weird word. So if I didn't spell it right, don't torture me. But you get the idea. This is the engineering piece of the design, right? Implementation is one thing. Understanding the full functionality of the protocol is another thing. So it's a very important concept. All right. So EIGRP was developed as a routing protocol. One of the things that I want you guys to understand, which they don't discuss in the book, but I think it's really important, is what is the difference between different types of routing protocols and how they make their routing decisions. And that is a concept that I think is important as well. Let me open up another Notepad document here. Dynamic routing protocols are classified into various categories. Now, this class doesn't really talk about this because they assume that you learned this in the CCNA, which you guys probably did. But I like to kind of refresh this information. There are classful versus classless routing protocols. All right. Classful is bad and classless is good. Ultimately, all it means is that classful routing protocols like RIP version 1, IGRP, EGP, etc. No, I guess that's pretty much it as far as the mainstream protocols. Do not send mask information along with the routing updates. As such, these protocols do not support subnetting. At least not in any way that would be useful. There was a RFC that was released. It was in 1993, I believe. Let me pull up the CIDR RFC. I'm pretty sure it was in 1993. Yeah, September of 1993. There was an RFC that was released called the CIDR RFC, or Classless Interdomain Routing RFC. And essentially in this RFC, they talked about essentially how do we fix this IP lack of IPv4 address space. And what they said was, let's come up with a way of, and this section here specifically it discusses that. Let's come up with a way to allow routers to advertise prefix information or prefix length information along with the network information. And that's where classless routing came into play. Classless routing protocols like EIGRP, RIP version 2, and then of course all the IPv6 versions of these protocols are classless because there were never class definitions in IPv6. EIGRP, RIP version 2, OSPF, BGP, these are all my classless routing protocols. They support subnetting. All right. And obviously that's going to be pretty important in a modern design because we want typically to have subnets. We don't want to have to be bound to Class A, Class B, Class C subnet mask prefix length information. Another classification is IGP versus EGP. Is it an interior gateway routing protocol, or is it an exterior gateway routing protocol? Okay, interior versus exterior. An interior gateway routing protocol is a protocol that you run this inside of your enterprise. So OSPF, EIGRP, ISIS, RIP, these are all interior gateway routing protocols. Exterior gateway routing protocols, you run this between autonomous systems on the internet. So this would be like BGP. All right, so typically you're not going to run BGP inside of your enterprise because it's a protocol that is designed to run between autonomous systems on the internet. Okay, so that's another kind of classification of protocols. Another classification or another differentiator between dynamic routing protocols is obviously whether or not they're open standard or proprietary. EIGRP is still somewhat considered proprietary because just because Cisco has allowed that protocol to run allows other vendors to implement that protocol, are you going to see Juniper or these other competitors implementing EIGRP on their platforms? Maybe, maybe not. But the final classification, and this is the one that I have to kind of drag you through real quick, is, and I'm trying to think of the term that I would use to describe this, but is it a distance vector routing protocol? Is it a link state routing protocol? Or is it a path vector routing protocol? So RIP, all versions, IGRP, which is a legacy, the precursor to EIGRP, doesn't really exist anymore. EIGRP, with a little asterisk there, are all distance vector routing protocols. All right. Now, we'll talk about what that means in a minute, but it's a really important concept because the fact that those protocols are distance vector means that they have to have other features built into the protocol that allow them to function because they're distance vector. Okay? And I'm going to use a diagram to explain the difference between distance vector and link state. ISIS, by the way, ISIS is classless as well. I guess I should put that up there. Intermediate system to intermediate system. I'll put the dash so we don't think we're talking about ISIS, okay? But ISIS is intermediate system to intermediate system. Still a protocol that's around, still used. OSPF, these are considered link state protocols, and BGP is what we would define as a path vector protocol, but from the perspective of AS routing, it is like distance vector. So going from one AS to the other, it is like a distance vector routing protocol. But we, most people will classify it as a path vector routing protocol because it uses path attributes to make its routing decisions. There's 12 or 13 different steps in that process. When we get into our BGP discussion, we'll get into that a little bit later on. Okay. There was one other thing I wanted to mention. Well, let me first, before I do that, let me explain the difference between distance vector and link state. Okay. You probably won't see any of these discussions on the exam, but I think it's important that you understand the difference because it actually changes essentially how the protocol functions. For example, EIGRP has something called a successor, feasibility condition. These are all functions, particularly the feasibility condition, are functions that have to be built into the protocol because it is distance vector. Split horizon, poison reverse, route poisoning, also functions that get built into protocols because they are distance vector. So let's say that I have a topology, all right, and I'm running, in this particular case, a distance vector routing protocol. We'll just call it EIGRP. All right, this is R1, R2, R3, R4, R5, and R6. And we are trying to reach network X from R1. Okay? Now, ultimately, what routing is always about is what is the next hop for a particular destination, right? R1 is not concerned about defining the entire path to reach R6. R1 is simply concerned about, do I send the packet there or do I send the packet there? And that doesn't change, based on any routing protocol. OSPF does the same thing. EIGRP does the same thing. RIPNet does the same thing. And actually, when you look at a routing table, that's what's defined in the global routing table is what is the next hop? How do I reach that destination? And then once that packet goes to the next router, it's up to that next router to make a decision on how they're going to route. So in router 1, I have to build a routing table that defines network X goes to next hop 3 or whatever. Router 3 or the next hop for router 2. Routing is always about sending the packet to the next router. Once that's done, unless you're doing policy-based routing, then it's a little bit, even with policy-based routing, you're still defining the next hop. You're just not using a dynamic process to do that. So somehow, R1 has to learn about network X, and that's where dynamic routing protocol exchange comes into play. Network X is attached to router 6. So ultimately, router 6 is going to advertise network X to its peers. And that advertisement is going to include some sort of metric value. Whatever, depending on what protocol we're using, etc., will determine what that metric is, but there's some sort of metric to reach network X. Okay? Now, I'm not going to do this in both directions. I'm only going to do this in one direction, but ultimately, router 5 might also advertise network X, because technically router 4 has two ways to reach network X, doesn't it? It can go through router 5 or it can go through router 6. So if we're using EIGRP, EIGRP is going to make a decision. It's going to say, okay, do I choose this path or do I choose this path? And typically it's based on said metric value. I'm going to choose one path or the other. Whichever one is the lowest value wins. All right. So what goes into the routing table for router 4 is the path that was selected. So let's say, for example, I selected that path. That's what's going to go into the routing table of router 4. Now, what's ultimately going to get advertised to the next router is not all the paths that router 4 learned about. This is a distance vector concept, but only the path that is being used. So XM, of course, that metric is going to increase because we're adding another link to the path. That route that gets advertised to router 2 is only the route that I'm using, not this route. So, but if you think about it, that kind of makes sense, doesn't it? I mean, router 4 should be making the best decision on how to reach network X based on metric. Does router 2 really care about that other path on router 4? No, because router 2 can't even use that path. But the downside to this is that router 2 does now does not have complete visibility of the topology. Router 2 is making a routing decision based on something called routing by rumor. And the same thing would happen in this case. Router 5 would advertise network X based on the route that it chose. Let me choose a different color here. And router 2 is going to have to decide, do I use this route or do I use this route? And again, that's just based on a standard metric value. That route's going to get installed. However, and that route that gets installed is whichever route I chose, right? That's the route I chose. I'll just put another circle here. Let's say I chose that path. So by the time I get to router 1, router 2 is advertising to router 1 only the path it chose, even though it learned about multiple paths. Router 3 is advertising to router 1 only the path it chose. Of course, router 3 only has one path, so that's ultimately what's going to get advertised. But from the perspective of understanding of the topology, in essence, all of this stuff from router 1's perspective is invisible. Unless we're advertising those specific links, I don't need to know what the details of those intermediate links or transit paths are to be able to get to network X. But R1 is making a decision on how to route, not based on an understanding of the entire topology, but based on an understanding of what router 2 and router 3 told it. Does this make sense, guys? I want to make sure that this makes sense. This is called routing by rumor. All right? And the issue is that because router 1 does not have a complete picture of the topology, there are additional features that have to be built into the protocol that allow that protocol to make good decisions. All right, to make good decisions, and we will see what that looks like. I'm just seeing if anybody is sending me any messages. Nope. Okay. What that looks like from the perspective of the decisions that the router is making. Now let's reverse this. Okay. And let's say that we're now running OSPF. That's as far back as I can go. OSPF is what we consider a link state routing protocol. It is a link state routing protocol. So every device is compiling something called an LSDB, or a link state database. Oh, and by the way, it was called distance vector before because I know the metric, which is the distance, and I know the direction I'm going, which is the vector. But I don't know anything else out here. I just kind of know how far it is, and I know what direction I want to go, but I don't know what's in between. Okay? That's why it's called distance vector, because I know the distance and the direction. OSPF and ISIS are link state routing protocols. Link state. So we're going to compile a database of the state of all of the links in the topology. So router 6 is going to advertise to router 4 and 5 not only network X, but the state of all of the links that are attached to router 6. Okay, there's different link state advertisement types: type 1, type 2, type 3, type 4, type 5, type 6, type 7, type 8, type 9, 10, 11, and 12. But we'll get into that when we get into our OSPF discussion. Router 4 is going to compile that information into its link state database. So router 4 knows not only about network X, but it also knows that router 6 is attached to that network and router 6 is attached to that network. Router 5 will advertise its link state information, which includes all of those links. That will also go in that database. Router 2 will advertise the state of all of its links. That will also go into the database. In fact, every router will advertise their link state information. And that information gets compiled. So by the time I get to router number 1, I have this database of every router in the topology, what links they're attached to. So in essence, I have a complete picture of the topology. And I can then make my own decision. Do I want to choose that path? I can evaluate every single path to that destination, and I can make a decision. I just deleted the whole thing. Let me see if I can. There we go. I can make a decision as to which path I want to use. Does that make sense? So I'm not relying on somebody else's decision. I'm making my own informed decision on how I'm going to reach that destination. Now, ultimately, that decision is still next hop. You know, we're not choosing the whole path. We're evaluating the whole path to decide what the next hop is going to be. But even link state routing protocols route to the next hop. They don't do, ultimately they don't decide what the entire path is going to be. Okay? So that is fundamentally the difference between a distance vector protocol and a link state routing protocol. I know it's not in the book, but honestly, I think it's important to understand those concepts because it really does affect how the routing protocol functions and how it makes decisions and so on. All right, so now we've got all the backstory. We can now go back into our EIGRP discussion and really start to look at the functionality of EIGRP. The diffusing update algorithm, as I mentioned before, is the algorithm that we use in EIGRP to make our decisions. We haven't talked about the components or the elements of that algorithm quite yet. We haven't talked about what a successor is, what a feasible successor is, what feasibility condition is, and so on. All right? But we will get into that a little bit later on. All right? I don't want to overwhelm you with too much information right now. All right? Hold on one second. Let me just send a message. All right. So we will get into that successor, feasible successor, feasibility condition, etc. A little bit later on. And of course, the metric as well. EIGRP uses a very complex metric. It does mention that it's composed of bandwidth and delay, but it's actually more than that. It is comprised of K values, K1, K2, K3, K4, and K5 for EIGRP for IPv4. And then we add a K6 for IPv6. And it looks at things like bandwidth, delay, reliability, and load. MTU is not part of the metric per se. It's used as a tiebreaker in the event that there are multiple paths that have a tie. But we'll get into that a little bit later on. All right. I'm just kind of summarizing what's in the text here. Originally created to route for IPv4, IPX, which was the Novell Layer 3 protocol, AppleTalk, which was Steve Jobs' Layer 3 routing protocol, or routed protocol, I should say. Those don't exist anymore. Everybody kind of solidified on IPv4. But EIGRP for IPv6 works as well. We're also going to see in this class, which we don't look at in the CCNA, what we call classic EIGRP configuration, router EIGRP, put in your network statements, etc., versus EIGRP named mode. All right, address family mode. Some people call it address family mode, which in the context of EIGRP is more of a kind of a consolidation feature to configure the EIGRP elements. In OSPF, it actually is much different because it combines the protocol stacks V4 and V6, but we'll see that when we get into OSPF. So what are we going to do in this section here? We're going to look at the features of EIGRP. You can see there's a lot of bullet points here. Each one of these bullet points is a separate topic. We're going to look at how EIGRP ensures reliability. That has to do with the message types. What is an EIGRP acknowledgement? What is the RTP? RTP is a function of EIGRP, not the real-time protocol, but the reliable transport protocol. That's one thing I didn't mention, which I'll go ahead and put in here, is that these protocols, OSI model relevance, I guess I'll just say. So, for example, EIGRP and OSPF are network layer protocols. All right. EIGRP is protocol 88 and OSPF is protocol 89. All right. Now, what I mean by that is if you look at an IPv4 packet header, inside the v4 packet header, there is a field called the protocol field. Just like the type field that we saw in Ethernet told us what was encapsulated inside of the frame, the protocol field tells us what's encapsulated inside of a packet. In other words, what's in this data field. Protocol 88, Protocol 89, EIGRP, OSPF, Protocol 1, ICMP, etc. Whenever you see a protocol or an application that has a protocol ID, that means that there is no layer 4 component. It is a layer 3 protocol. TCP is protocol 6, and UDP is protocol 17. So those are additional protocols. Interestingly enough, ISIS is a layer 2 protocol. Well, I'll just say data link layer to be consistent protocol, meaning layer 2. It's kind of interesting if you think about it because, you know, it's a routing protocol, right? The whole point of ISIS is to exchange network layer reachability information, but it functions at the data link layer, so it doesn't even have a packet header. ISIS frames are they're framed in I think they're framed inside of 802.3. Let's take a look real quick. Even though we don't really talk about ISIS PCAP, we don't really talk about ISIS too much. But let's take a look at what an ISIS encapsulated frame looks like. I think it's in 802.3, if I'm not mistaken. It could be Ethernet too, but well, nice thing is this, we can just kind of go and check. All right. So, well, that's HDLC. That's a serial encapsulation, which actually is not uncommon because ISIS is typically used in a serial environment. So that's not going to help me. I need I'll bet all of these are probably going to be serial. I mean, it's not important for our discussion, but, you know, whenever I think of something and I don't know the answer exactly, I kind of want to take a look. There we go. It is, in fact, 802.3 Ethernet. Okay? Notice there's no packet header here. So if anybody argues with you and says, no, ISIS is definitely a layer 3 protocol, it exchanges layer 3 reachability information, routing tables, but it operates directly on top of layer 2. All right? If you look at the DSAP and SSAP, it's ISO network layer, which International Organization of Standardization, which is essentially what ISIS was developed under, and this is the ISIS payload. If it was a layer 3 protocol, you'd see a packet header. You would see a packet header. All right. Well, guess what? Let's take a look at a RIP PCAP. All right. Because interestingly enough, RIP and BGP are applications. They run, they operate, they are protocols that operate at layer 7. Okay? RIP uses UDP, depending on the version of RIP, but I'll prove it to you. If I open up a RIP PCAP and I go into any of these RIP messages, there's layer 2, there's layer 3. The protocol field in layer 3 is 17, which is UDP, not RIP, right? And there's UDP, specifically port 520. Anything that runs on top of UDP or TCP is considered an application because it's above layer 4, right? So, that being said, UDP 520 for RIP for IPv4 and UDP 521 for RIP for IPv6. What about BGP? BGP is a TCP-based protocol, so it's also an application. Let me go out and grab a BGP PCAP. Remember I was talking yesterday about how important it is to kind of, look at Wireshark captures, because they give you, let's get, well, it doesn't really matter. Yeah, we'll just download this one here. There's lots of different message types in BGP, but all we're looking at is what is it transported over, right? This is a BGP update TCP, specifically port 179. So again, BGP uses TCP port 179, and as such, it's defined as an application layer protocol. The only reason I mention that, it's not going to be on the test, but the only reason I mention it is because it's, again, we're putting the pieces together. Understanding these protocols is not just about router EIGRP 100, network 10, whatever. It's about understanding the design. All right? Troubleshooting configurations is one thing. Troubleshooting the design is a completely another thing. So a little bit of a side topic there based on what we were talking about. We're going to take a look at how EIGRP adds routes to the routing table. We're going to describe the named mode configuration versus classic mode. We're going to also talk about what is configured under different address family modes, how EIGRP neighbors exchange information. So in that case, we're going to be talking about things like the message types. What is an EIGRP update? What is a query? What is a reply? What is an acknowledgement? How do I choose the best path? That's going to be primarily based on what is the metric. And that gets into the metric calculation. What is feasibility condition? That's part of the dual algorithm. This piece has to be here because of the fact that the protocol is distance vector. That piece has to be there. And then also we'll take a look at the EIGRP path selection process. So lots and lots of interesting things that we're going to talk about here in this section. All right. So let's start, and of course we'll do our discoveries, which allows us to kind of solidify this based on our configurations. What are some of the features of EIGRP? I'm going to summarize, in essence, everything that they're talking about down here in this section. And then, some of this we've already kind of talked about. Some of it we haven't, right? We talked about this piece. Ooh, that's a little big there. Sorry about that. We talked about this piece, VLSM, variable length subnet masking, meaning subnets. EIGRP is a classless routing protocol, so it supports subnets. Data link protocol support. What they mean by that is that it will operate over frame relay, it'll operate over Ethernet, it'll operate over PPP, HDLC, and it pretty much functions in every case. There might be some different things you have to configure to allow that to happen, but it doesn't really care what the data link layer transport is. It will still operate. All right. There is EIGRP for IPV4 and EIGRP for IPV6. In essence, they're configured the same way. They build the exact same data structures. The metric is calculated the same way. The only difference in IPv6 is we have 6K values instead of just 5. Very fast to converge. I'll put a little star there. All right. EIGRP is actually a very efficient routing protocol as long as it's implemented correctly. You can implement EIGRP in a not so good way that causes it to converge less quickly, or you can implement it in the optimal way, which means it would be one of the fastest converging routing protocols that are available, even faster than OSPF. And we'll talk about that when we get into some of the different configurations and designs. There are several things that you consider when you're trying to decide what protocol you're going to use in your enterprise. Convergence speed is one of those things. What does it mean to converge? When we say convergence, what does that mean? If something changes in the topology, how long does it take for everybody to be aware of that change and for the network to respond to that change? If a link goes down and I have to reroute traffic over another link, how quickly does that happen? That's what convergence is. All right, kind of what you were describing, right? You want a protocol that's going to converge quickly. You don't want a protocol that's going to take 1 or 2 or 3 minutes to figure out what the heck is going on. You want a protocol that's going to converge very quickly. And EIGRP does that if it's designed correctly. Partial updates. We mention this because some of the older distance vector routing protocols like RIP would send out their entire routing table on a periodic increment or a periodic interval every 30 seconds for RIP. When should I have to send out an update? When something changes, right? I don't need to send out my routing information every 30 seconds. You already have my routing information. If it hasn't changed, then just assume it hasn't changed. I don't need to waste bandwidth and resources to keep telling you, right? It's like saying, are we there yet? Are we there yet? Are we there yet? Are we there yet? I'll tell you when we get there, all right? You'll know when we park, right? Same kind of concept. So in EIGRP, we don't do periodic updates. We do incremental updates. Incremental updates means we send out updates when something changes. OSPF is the same way. But also, we only send the changes, not the entire database. I don't need to tell you about the whole database. I already told you about that when we initially converged and formed our adjacency and shared our information. So I'm just going to update you on the changes. Now, OSPF does have a periodic feature. Every 30 minutes, the link state database is flooded. That's called a paranoid update. But most people classify OSPF as a incremental protocol because outside of that periodic update, that paranoid update, I should say, it does do incremental updates. All right? All right. 32-bit wide metric or a 64-bit wide metric. We use the 32-bit wide metric when we're running classic mode EIGRP. We use a 64-bit wide metric when we go to named mode. And that's important, actually, because the metric field, you know, we've had in the past when this protocol was invented, not in 2013, I think it was 1991 or 92, was the original publication of EIGRP. We didn't have gig links, 10 gig links, terabit links, 10 terabit links, etc. We had serial connections, 1.544 meg, 10 meg, maybe 100 meg. So a 32-bit wide metric was fine to differentiate the value for those particular interfaces. But when you go to a more modern network where you have all these different speeds, there wasn't enough space in the metric field to differentiate between all these different interface types. So we had to go to a 64-bit metric to be able to differentiate all those different network types. We'll actually see some calculations of that a little bit later on. All right. Here they're just describing the fact that EIGRP was published as an open standard, opening other vendors to promote interoperability. But it is a kind of a scaled back version of EIGRP. Like, I believe, if I'm not mistaken, things like the stub routing feature are not included in that openness. But, you know, in the past, people would kind of stay away from Cisco, or they would stay away from EIGRP because it was proprietary to Cisco. All right. Now, remember I put a, let me see if I can find it here. I put an asterisk. Where is my distance vector link state? Not on this page. Let's see. Right here. I put a little asterisk here for distance vector. EIGRP fundamentally is a distance vector routing protocol. It does routing by rumor. There's no way to get around it. That's what it does. But it does incorporate a lot of link state properties. You know, things like incremental and periodic, or incremental updates, partial updates, and so on. So a lot of times people will simply classify EIGRP as an advanced distance vector routing protocol. Most people would stay away from distance vector. Routing by rumor, don't have a complete picture of the topology. Nah, I don't want to use it. RIP is purely distance vector, and we tend to stay away from RIP for that reason and many other reasons. But EIGRP is advanced distance vector, and they classify it as advanced distance vector simply because it incorporates a lot of the convergence features that link state has. Fundamentally, though, it is still a distance vector routing protocol. Fundamentally, it's a distance vector routing protocol. All right? All this stuff we already kind of talked about. VLSM support, sophisticated metric. Yeah, so again, that wider metric, that new metric format, allows us to go above 1 gig all the way up to 4.2 terabits. So eventually they'll probably gonna have to change it again. You know, and they do RFC updates and whatnot for the protocols. All right. Next section here is what is RTP? What RTP is not is a separate protocol. They identify it as the reliable transport protocol, but if you look at an EIGRP packet capture, you will never see RTP. So it's an interesting concept. I haven't really done any research on this and tried to identify why they always seem to classify RTP as a separate protocol. To me, it's more of a function of EIGRP in that EIGRP is reliable. Remember we had the 5 basic message types: hello, update, query, reply, and acknowledgement. 3 of those 5 message types get acknowledged, meaning that if I send you a query, you're going to acknowledge the receipt of that query. If I send you an update, you're going to acknowledge the receipt of that update. If I send you a reply, you're going to acknowledge the receipt of that reply. That is the reliability component. Why do we mention this? Because EIGRP runs directly on top of IP. And IP is known as a connectionless protocol. There's no sequencing, there's no acknowledgments, there's no three-way handshake. IP is send it and forget it. If it gets there, it gets there. If it doesn't, it doesn't. So RTP provides guaranteed delivery, etc. But again, it's not, you're never going to see a separate kind of RTP transaction. It just happens to be built into the protocol. All right. Let me see if I can show you that real quick. So let's pull up an EIGRP update PCAP. We'll see, of course, this later on. Subnet down, goodbye. All right, subnet up will work because that's an update. And what you'll see in this, I'm not going to get into the specific details of of what an update is. We'll get into the actual details of the packets themselves later on. But look at what's in the EIGRP header. Sequence numbers and acknowledgements. So that's the RTP function. Sequencing, of course, allows me to identify the order delivery of datagrams. And the acknowledgement, this is not an acknowledgement, so that flag is not set. But the acknowledgement, or that field is not set. It's not a flag. It's a 32-bit field. That acknowledgement field allows me to acknowledge the receipt of something. So, for example, I saw an acknowledgement up here. Well, this is a hello. Is it also? They classify hellos and acknowledgements as the same packet type, same opcode. This does happen to be an acknowledgement because it's marked as an acknowledgement. You know, the point is that is that's that ordered packet delivery, guaranteed delivery. It's built into the EIGRP packet header. Okay. EIGRP supports both multicast and unicast traffic, as well as multicast and unicast adjacencies, but we use multicast to deliver our EIGRP messages. There are some instances where we will use unicast, but we use multicast to deliver, and you can see that here, destination, multicast, multicast, multicast. Remember, 224 is all my well-known multicast addresses, and .0.0.10 is reserved for EIGRP. Okay? Only selected packets are sent reliably. Well, out of those 5 packet types, hello, update, query, reply, and acknowledgement, the ones that are acknowledged are updates, replies, and queries. I mean, it makes sense, right? We're not going to acknowledge an acknowledgement. That would be a circular function. And hellos are just a way for us to essentially identify ourselves to our neighbors, to form adjacencies, and to maintain those adjacencies. So I send you a hello, you send me a hello. We don't acknowledge hellos. Okay? All right. Very similar in OSPF. LSAs are acknowledged. LSRs are acknowledged. And database descriptor packets are acknowledged, but not acknowledgements and not hellos. All right? We don't need acknowledgements with BGP because BGP runs on top of TCP, which includes sequencing and acknowledgements in the protocol, TCP. All right? And then for IPv6, it's FF02:A. FF is multicast. 0 is, oops, I didn't want to do that. Let's see. Undo that. 0 indicates the whether it's a well-known multicast address or whether or not it's a locally configured multicast address, and 2 represents the scope. This is a link local scope for the multicast packet, and then A is the group number, :A, which, by the way, is hex for 10. So it matches. All right. For efficiency reasons, RTP sends only certain packets reliably. We talked about that. And of course, we are going to get into, as we go through the rest of our EIGRP discussion, we'll take a look at what a hello looks like. We'll take a look at what an acknowledgement looks like, etc. All the packet types. We're going to look at all the different packet types. So this is, in essence, the adjacency process. Router 1 and router 2 are configured for EIGRP. Now, there's a few things that have to be, set up correctly on those routers for them to be able to form an adjacency. They have to be in the same autonomous system. They have to share a common subnet. They have to have the same authentication. They do not have to have the same timers. But we'll get into that later. I don't want to put everything on this slide. But in essence, once you've enabled EIGRP on an interface, that interface is going to start generating these hello packets. And if you look at an EIGRP hello, let me get rid of that. It is pretty basic, right? First of all, it has, by the way, from here to here, let me draw a line. This is the EIGRP header. One of the things that you will see is that every single EIGRP packet, updates, queries, replies, hellos, acknowledgments, has that in the header. Okay? This is the actual EIGRP data. So just keep that in mind. OSPF has its own header. EIGRP has its own header. BGP has its own header. And that's common to every packet type. In this case, this is the version of EIGRP. Is it EIGRP for IPv4 or IPv6? This is the opcode, which tells us essentially what type of EIGRP packet this is. Is it a hello? Is it an update? Is it a query? Is it a reply? Checksum is a way for us to verify the integrity of the data. It's a mathematical check, or a cyclic redundancy check, or a hash, if you will. It's not really a hash. It's actually a CRC, but it's similar to a hash. And by the way, if you see anything in brackets in Wireshark, that is something that's added by Wireshark. That is not part of the header. Okay? So anything in brackets is not part of the header. You've got various flags here. All right. We don't really care about the flags right now. And typically when you get into the CCIE level, you start to talk about those types of details. No sequence number, no acknowledgement, because hellos are not sequenced or acknowledged. All right. If I was running address families and VRFs, I'd see some virtual router information there. This is the autonomous system that EIGRP belongs to. This particular router belongs to. An autonomous system is a group of devices that talk to each other. In EIGRP, that number has to match in order for the routers to be able to communicate with each other. So that's a pretty important concept. All right. And then we see what is the information that's actually contained in the hello. Kind of important, actually. What are my K values? So it looks like this is EIGRP. Why do I have a K6? This is V4. Maybe it carries it even though it's not used in IPv4. K6, well, actually, this is probably named mode, a named mode configuration, because you might, I believe you see the K6 in named mode as well, but we'll get into that later on. Bandwidth, delay, reliability, not right. K1 is associated to bandwidth. We'll talk about the K values when we get into the metric. But K1 and K3 are tied to bandwidth and delay. These are essentially values that we can assign in EIGRP to apply different weights to different components. So if I want bandwidth to count more, I could assign a higher K value to bandwidth, and it would count for more in the calculation of the metric, and so on. But those K values have to match. Autonomous system has to match. If the K values don't match, we cannot form an adjacency. All right. Hold time, 15 seconds. All right. Hold time, if I become a neighbor with you, I have two values. I have an update or a hello interval, and I have a dead time or a hold interval. And typically in EIGRP, it's 3 times. In OSPF, it's 4 times the hello interval. So the hello interval for EIGRP is 5 seconds. Every 5 seconds, I'm sending a hello packet. Right? Do we have timestamps? Yeah. Because they're using epoch time. They're not using actual time. Well, actually, let me see here. Yeah. 2-6. So this hello is at 2.09. This hello is at 6.35. It also depends on how. Oh, that's an update. Excuse me. Here, let's apply a filter. Selected. 2.6.3. Yeah. It's about right, right? So you've got a hello here at 2.09, 6.36, 11.09, 15. That's about 5 seconds apart, right? Give or take. But it is every 5 seconds. And the hold time in this case is 15 seconds. You can modify those timers. That's hello and that's hold. So essentially what happens is when I form an adjacency with a peer, I expect to get a hello every 5 seconds. If I miss one, okay, no big deal. You still got 10 more seconds to send me one. If I miss 2, okay, no big deal. You still got 5 more seconds to send me one. If I miss 3, you ain't there anymore. So I'm going to delete my relationship with you. I'm going to delete the adjacency. That's what the hold timer is for. The hold timer allows us to define how long I'm going to hold that adjacency if I don't hear anything else from you within that time period. I will delete you as a neighbor. Okay? That time does not have to match. We'll talk more about what happens when it doesn't match. And then I get some other information about what version of EIGRP you're running, and what release and so on. There are some restrictions as to versions and EIGRP routers being able to communicate with each other. Now, obviously, that's not the point of this slide here, is to look at a packet capture, but I live by packet captures. Because if you can go through a packet capture and identify every piece of that packet capture, then you understand the protocol, because that's literally the data that's being sent by the device. Okay, so hey, I'm a router. This is my autonomous system number. These are my K values. This is my authentication. Would you like to be my neighbor? Okay. Oh, by the way, I'm sending you a hello, and here's all my information. Would you like to be my neighbor? As long as the parameters that are necessary match, we become adjacent. EIGRP, it's pretty much the adjacency is there or it's not there. In OSPF, we go from down to init to two-way to xstart to exchange to loading to full. There's a whole transition of relationship. OSPF is a little bit more picky, I guess, in how it establishes adjacencies. So that is the first step in EIGRP routers being able to communicate to each other. They have to become neighbors. R2 has to be listed in R1's neighbor table. R1 needs to be listed in R2's neighbor table. By the way, guess what these three tables are? We talked about that in the beginning of our discussion. These are the data structures. Once we've established that we are neighbors, we now share routing information. Remember, these are acknowledged. What do you think is in an EIGRP update? We just happen to have one right here. Okay. So we still have our header. So from autonomous system up to version, that's my header. Notice that I've identified a sequence number for this update. And look what's included in the update. Prefix information, network layer reachability information. 192.168. I'm advertising that I know how to get to 192.168.4.0. Prefix length is 24 bits. I am the next hop, so I'm advertising myself as the next hop. This is the delay. This is the bandwidth. This is the reliability. These are all the metric values for that particular path. And I've got some other flags. Again, that's more CCIE level. But in essence, an update is basically me telling my peer what I know about. In this case, I know about 192.168.4.0. This is an EIGRP internal route, not a DEX route, which is a redistributed route in EIGRP. We'll talk about redistribution later on as well. All right. So, I mean, that's an update. An update is just me telling the router about networks that I know about. Okay. And by the way, that update includes the metric information based on the route that I've selected. I take that information from that peer, and that goes into my topology table. The topology table is everything that I've learned. This is my EIGRP rib. Okay. Send the acknowledgement. Thank you for that update. I appreciate it. Guess what? There's the acknowledgement. What do you think the acknowledgement number is going to be for this? 45. I am acknowledging sequence 45. Notice that an acknowledgement doesn't contain any data. All it contains is a header. The EIGRP header. But this is the field that's important. This is the field that identifies to the peer, I received sequence number 45. And I believe, don't quote me on this, but I believe the sequencing numbers are based on the amount of data that's been processed. I know that's how it works in TCP. It's byte count, but I've never really kind of analyzed whether or not that's the case for EIGRP. This peer is going to send an update. Here's my routing information. That goes into that topology table. I run my algorithm against that information, and I extract from that topology table my global rib. I'll just put a G for global. I extract the routes that I'm actually going to use. Just because a route is in the topology table does not mean that it goes into the routing table. We don't really get into that stuff in this class. The concept of longest match routing, administrative distance, etc., because they kind of assume that you already know that, and they focus on the protocols in this class. If I have a chance to go back to that later on, I will. And of course, we acknowledge that update. So looking at this sequence of events. If you were troubleshooting EIGRP, maybe you're not getting a route in the routing table. What do you think the first thing that you're going to verify is? Do I just immediately start troubleshooting the routing table?
You probably start up the topology table first, right?
Neighbors.
Why neighbor over topology?
Because the only way stuff goes into the topology table is if you have neighbors. So for me, if I'm not learning routing information, the first thing I'm looking at is that neighbor table. Do I have the neighbors I expect to have? Then I would go and look at the topology table. Am I learning everything that I should be learning in the EIGRP process? There's many reasons why routes might not go into the routing table, and it might not actually be a problem with EIGRP at all. It could just be that we had a static route that matched the EIGRP route, and static routes have a lower administrative distance, so that got chosen. But, you know, logically speaking, this is it's kind of a building process, right? We get our neighbors first, the neighbors who we're learning everything from. That information goes into the topology table. Then we run our algorithm, we extract the information from the topology table, and that goes into our routing table. Okay? By the way, OSPF, same thing. Neighbor table, topology table, routing table. BGP, same thing. Neighbor table, topology table, routing table. So we're spending a lot of time on this topic here, but I just can't stress enough how important it is to have this foundation knowledge to be able to walk away and say, you know what? I not only know how to configure EIGRP, but I know how it works, right? Which is why we never end up finishing all the content in this class, because I just talk too much and go into so much detail, okay? Here they're just describing the process, right? Which we obviously went through quite a bit of detail. All right. Now, when we're implementing EIGRP, we can implement EIGRP in one of two modes. Most people are familiar with the classic mode implementation. You know, where you do router EIGRP, you put in your network statements, you configure the properties of EIGRP. If you're doing authentication, that's done at the interface level. If you're doing route summaries, that's done at the interface level. If you're doing advertising or joining particular networks or enabling EIGRP on an interface, that's done in the global routing configuration level or the EIGRP routing configuration level. So the problem with classic mode is that you have a scattered configuration. Some of the configurations go into the interface, some of the configurations go into the routing configuration, and so on. And also, the syntax is slightly different for IPv4 and IPv6. Similar, but different. Not the same. Okay, what happens when we go to named mode? And by the way, they should really add a 32-bit wide metric here, because that could potentially be a problem, right? And they should add a 64-bit wide metric here, because that's a better solution. But with named mode EIGRP, all of the configurations are done under the EIGRP address family configuration in one place. Authentication, summarization, modifying or stub routing features, whatever it is that you're configuring with EIGRP, it all happens in the same context, the same block. We unify the configuration of EIGRP, meaning that the commands are the same. The structure of the commands are the same. It is backwards compatible, albeit you have to kind of worry about this a little bit, but a named mode EIGRP router can talk to a classic mode EIGRP router. high-speed support for high-speed links. I guess that's the 64-bit metric. They didn't mention it specifically, but we have support for these higher speed links because we have a wide metric. In classic mode, we use microseconds to identify delay. Microseconds is good, but you start to get to faster and faster and faster interfaces, microseconds becomes a little bit less accurate. So they now have picosecond latency, which is the delay calculation. Okay? And there is a conversion tool. There's a command that you can actually run if you've already configured your router in classic mode that will automatically convert that configuration to named mode. You won't have to retype the commands. We'll actually see that command here in a little bit. All right. In fact, it's right here. EIGRP upgrade CLI. All right. EIGRP upgrade CLI. Now, as far as knowing that command, that's probably not going to be on the test. Also knowing when named mode became available, 15.01M for iOS XE, 12.2.33 SRE for standard iOS, but again, we don't really need to know that. Okay. The main thing is that EIGRP named mode gathers all of the configurations in a single place. All right, and we'll see that. We're going to do the configurations. That's part of our discovery that we're going to be doing in a little bit. Here's kind of an example. All right. Now, it takes a little bit of getting used to. If you're used to configuring EIGRP in classic mode, you'll see some of the commands. You'll recognize the commands like summary addresses for EIGRP summaries, authentication, modifying the timers, no split horizon, which is a distance vector loop prevention mechanism with distance vector routing protocols, passive interface. All of these commands exist in classic mode. It's just a matter of how they're configured in named mode. If you see AF interface, that would be a command that would typically be implemented under the interface in classic mode. So doing things like EIGRP summaries, authentication, modifying timers, that's something that's done in classic mode under the interface. So literally config T, interface Ethernet 00, put those commands in. The syntax is the same. I would say summary-address and put that command in. But in named mode, we do it under what we call an AF interface, address family interface. Okay? This would be normally, if you did a show run, that would be what would show up under the interface typically in classic mode. Now it all shows up under the EIGRP Cisco section, which is named mode. All right. So you have your interface specific commands, and then you have commands that affect what I like to say affect the topology table, or affect how the topology table is constructed, which is why we're referencing topology base. We don't know what these commands do, and again, that's not the point of this. Looking at this, you're not supposed to understand what every one of these commands does. Normally, this stuff here would be done under router EIGRP. Right? You would set the variance. You would do redistribution, etc. Distribute list and redistribution. In addition, this stuff would also be done under router EIGRP. So if you look at this, there's actually 3 layers of hierarchy in address family mode. There is the global configurations that are applied to address family IPv4. Those are the red ones, kind of our general configurations. In this case, our stub routing features, our network statements to enable the protocol and the interface, and so on. We have number 2, that's number 1, global, right? I'm kind of going backwards. Number 2 is anything that affects the topology table. The reason I'm breaking this down is because a lot of times when people are moving to named mode, they have a difficult time understanding. They understand the classic mode stuff perfectly, but they have a difficult time understanding what kind of configuration category it goes into in address family mode or named mode. If it affects the database, if it affects the topology database, metric, like setting K values, stuff like that, that goes under topology base. And if it's something that you would have normally entered in, on the interface in classic mode, that goes into AF interface. Another benefit to this named mode configuration. So let's say, for example, I wanted to put that summary on this interface as well. In fact, I wanted to put that summary on all my interfaces. I wanted to do this authentication on all of my EIGRP interfaces. There is an AF interface default. It's not listed here because they didn't use it, but you can actually create an AF interface called default. And anything you apply under that AF interface applies to every interface on the router. So that's kind of nice. You can, instead of having to duplicate configurations on every AF interface, you can just apply it to the default interface and it automatically gets duplicated. All right. Again, the point of this is not to understand the configuration, the commands. We'll get into that. The point is basically to understand the general configuration, which brings us to our first ENARSI discovery, configuring EIGRP using classic mode and named mode. All right. We're going to, yeah.
I'm getting an error when I try to load mine. It says could not bind to IP address.
Could not find what?
Could not bind the IMD to an address. Why would it open?
The file itself?
Yes.
Do you have 2 green dots?
No.
Well, that's a problem. We have to get that fixed.
I have the GNS running on.
Well, desktop will always run pretty much. If you don't have a green dot for GNS3 VM, then the lab will not load. Okay, did you launch your VM?
Mm-hmm.
Okay. You want to bring your laptop over here?
Yeah, I'll bring it right in.
All right. Because we're live streaming, so.
No, you can go ahead.
Well, no, you can bring it over. I don't mind. I'll take a look at it real quick, but I'll kind of do 2 things at once. I can talk and kind of play with it, see if I can get it working. Did you get any errors when you launched GNS3? Initially?
Well, that's running right now, but
All right, let's kill that. Cannot load GNS3 VM settings. 128. All right. I'm not even seeing your local server. right, let me have a seat. Give me a second here. I'll take a look at this. What I typically do is, and in fact, has a lot of experience with this, so she can kind of walk you through it. Is you might have to delete your VNet adapter and re-add one. But I'm curious why, because it is trying to bind to the right interface. But I'm curious why your local
Yeah, I
one.
haven't done anything different since yesterday.
I know. It's trust me. She's run into the same thing. The binding is not set up. Yeah, see, your binding interface is missing. So go ahead and she'll walk you through it. 'Cause I hate to put this on you, but if I wasn't live streaming, I'd take a look at it. But she knows exactly how to get that fixed. Basically, you have to shut down your VM, create a new VMnet adapter, and reassociate it, and then set it up again. But she'll be happy to help you with that. Well, maybe not happy, but I'm going to dump it on her anyway. She's only set up GNS3 about 10 times already this week, and it's only our third day. All right. I'll talk slowly to give you a chance to catch up here. But Discovery 1, as you can see in our topology here, we have 4 different routers. We have an HQ router. We have Ethernet 1.0 on BR1, BR2, and our distribution router. And in essence, a lot of these routers are already configured. I know it looks like a complex topology, but a lot of these routers are already configured. And we're either going to continue the configuration, or we are going to add the configuration or convert from classic mode to named mode. Now, I will, in this process, add to our discussion, because I want to show you guys things, even if it's not in the discovery, that I think are important to better understand the protocol and to better understand its functionality. All right. So it looks like in this case, HQ is running named mode, right? And it's running both V4 and V6. We can see that we are dual stacked here. We've got IPv4 and IPv6 enabled on all of these interfaces. BR1 is running classic mode, IPv6. BR2 is running classic mode, IPv4. And the distribution router isn't running anything. It's not configured at all. Okay? So our goal in this exercise, why did my text disappear? That's weird. Let me pause this. My CPU is only at 70%. I lost all my text. Let me kill Word here. What is going on here with my document? I'll kill that, and looks like it already closed. All right. Go back in here. All right. Now we're back in business. So we are going to enable IPv4 EIGRP using classic mode on BR1. BR1 is only running IPv6. We are going to enable IPv6 EIGRP using classic mode on BR2. You're good now? Awesome. Which is only running IPv4. We are going to configure V4 and V6 using named mode on the distribution router, which is an interesting point, right? I mean, normally you wouldn't do this. you wouldn't have some routers running classic and some routers running named. You would have, everybody running named or everybody running classic. But that's the point. They want to prove the fact that it's compatible. You can run both, and they can talk to each other. We want to configure BR1 and the distribution router to send EIGRP updates only through interfaces pairing with EIGRP neighbors. So that would be our passive interface command. And then we're going to adjust the hold times. It's good stuff, but lots of stuff to talk about here. All right. Now keep in mind on the topology, the interface numbers don't match. So make sure that you're looking at the interface numbers in GNS3. Okay. And this is all of our IP addressing information. We're good there. So, task number 1. So, I am going to, throughout this process, we're going to be doing the configurations, but I'm also going to be describing what the purpose of these commands are, even more so than what the book has. Okay? I want to, turn my interface devices back on. So we need to go into BR1, and they essentially want us to enable EIGRP for IPv4 using classic mode. Now, before we actually do that, what I typically like to do is, and this is like a Phillips head in your tool chest. You use it all the time. Show IP protocols. I like to see what's running before I do any implementations, because you don't want to go through and add additional protocols. You want to make sure that you are essentially, in essence, not creating a conflict, right? If some other protocol is running or something like that. Now, if I did show IPv6 protocols, we would see that EIGRP is running an AS20 for IPv6. There are my K values. So it is classic mode. It's not named mode. Named mode, again, adds that K6 value. So when we were looking at that Wireshark capture earlier, we saw K6. We knew that that was named mode. And so on. We'll talk about what all these values mean later on. That's part of our discovery. Okay, so config T, and we are going to go into router EIGRP, and we're going to select autonomous system number 10. So that's the first thing I'm going to talk about. What is the autonomous system number? And what does it mean to EIGRP? First of all, unlike BGP, where the autonomous system numbers have a specific meaning, are they global, are they local, kind of thing. In EIGRP, the autonomous system number is completely arbitrary. You can pick whatever number you want as long as it matches on the routers. The AS for IPv6 can be the same as the AS for IPv4. In this case, they're using 10. So we want to make sure that on all the other routers we use 10. It's that simple. There's no different meaning between 10 and 20. There's no different meaning between 10 and 65,535. But it's a 16-bit field, which means we're limited to, well, technically 0 through 65,535, mathematically anyway, but EIGRP doesn't allow us to use 0. Now, if I do show IP protocols at this point, you can see that by implementing router EIGRP 10, the routing process is now enabled on the router. All right? It's not routing for any networks, meaning it's not enabled on any interfaces, but it is, the process is running on the router itself. All right? And again, we'll talk about all these values, what all this stuff means in a little bit. The next thing they have us do is to do network statements. So now we have a sidebar conversation about what a network statement is. Network statements used in enabling IPv4 routing protocols, not IPv6. We don't use network statements in IPv6. Do the following. It tells the router which interfaces to enable the protocol. I don't want to end in a preposition again. I don't know why that particular vocabulary skill has stuck in my head, but tells the router which interfaces that the protocol is going to run on. Is going to, that's a preposition. Oh, screw it. I'm going to use a preposition at the end. All right. All right. Tells the router which interface the protocol is going to run on. All right. It does not define how networks are advertised. And what I mean by that is the routing prefix information. Think of a network statement as a light switch. Turns on or turns off the protocol on the interfaces. Excuse me. The networks, and I'll explain more about this visually when we go into our configuration. The networks that get advertised are based on what is configured on the interfaces that are included in the network statement. Okay? Network statements can be very specific, or they can be general. So I know there's several bullet points here. You might say, I kind of understand what you're saying, but I don't really understand what you're saying. Let's talk about what we're saying. Okay? If I do a show IP route connected, and I say include C, okay? These are the three interfaces on this router. If I wanted to run EIGRP on all three of those interfaces, I could simply put a network statement of 192.168.0.0, 0.0.255.255, right? We use inverse masks for actually EIGRP will accept a dotted decimal mask as well, and then it converts it to inverse. So that command enables EIGRP, so you already got an adjacency, on all three interfaces, because essentially what this command is saying is any interface that starts with 192.168. Zeros mean I care, ones mean I don't care in the mask. Now you guys can do what's in the book. What I'm explaining is how the network statement is formatted. Now, what I said was in my text document is the networks that actually get advertised are these networks. 1.0/24, 2.0/24, 255.0/30. All this did was turn the protocol on. So I could do that way. I could do it this way. Network 192.168, 1. Let me do my local routes. I could do network 192.168 1.1 0.0.0.0. What did that network statement do? It enabled EIGRP for autonomous system number 10 on the interface with that IP address. This is an exact match. 1.1 is loopback 0. And I could come in here and I could say 2.1 for loopback 1. And I could say 255.2, which is the one that would actually result in an adjacency. All right. So what's the best practice? Do I use kind of more generic statements or do I use more specific statements? If you're lazy and you want your configuration to be simple, use more generic statements. If you're concerned about security and specifically identifying which interfaces run the protocol, use more specific network statements. Okay? But it's a light switch. As long as the IP address on the interface is included in the range of the network statement, it turns on the protocol on the interface. A lot of people think that these network statements define what the router's actually advertising. That's not the case. It's always what's on the interface is what is being advertised. Always what's on the interface is what is being advertised. All right? So many ways to skin the cat, I guess. In this case, they opted to do a couple of different things. Here, they didn't even put a mask. If you don't put a subnet mask, EIGRP will assume the classful mask. It'll say, oh, 192 is a class C. I'm going to assume that the first 3 octets matter. Here they put a .3 mask, which is an inverse of a /30, which happens to be the prefix length for that interface. But again, this network statement doesn't define how the routes get advertised. It's just a light switch to turn on or turn off the protocol. Okay? They do describe that here. What is the AS number? Here they're describing what the what the network statement is, which we've already done. Okay. Step number 2. They want us to define a router ID. Well, now we have more notes. Router ID. The router ID, and this is all in the book. I just kind of like to summarize it separately as these bullet points. But the router ID essentially defines the router uniquely in the AS. Is that how you spell unique? I don't know. Don't ever challenge or don't ever punish me for my spelling. It's we all got so used to the red lines under the words, right? You don't really think about spelling anymore. You just look for those red squiggly lines and right click and fix it. Yeah. I think that's correct. But anyway, the router ID defines the router uniquely in the AS. So it must be unique, right? It's like a fingerprint. We didn't assign the router ID to this router. Not yet. That's one of the tasks they want us to do. But if I do a show IP protocols, you will see that a router ID is actually assigned. So if you don't statically configure a router ID, the router will pick its own router ID. Here is the order of operations for selecting the router ID. What takes precedence is if it's manually configured. right? So if you're statically setting the router ID, that's what the router ID becomes. If you haven't assigned a router ID, there are two more steps to automatically select the router ID. Number one, the IP address of the highest active loopback interface. Does not have to be part of EIGRP, but the interface has to be up. If you don't have a loopback interface, the IP address of the highest active physical interface. By the way, if you don't have a loopback interface and you don't have an active physical interface, then you have a paperweight. How's a router going to route if it doesn't have any active interfaces? Right? In other words, the router ID will always be selected. In our case, if I do a show IP interface brief, you can see, let's do pipe include up. You can see I have three interfaces here. Loopback highest, meaning numerically the highest. Not the loopback interface number, but the IP address. So 192.168.2 is higher than 192.168.1. That's how that became the router ID. Now in EIGRP, the router ID doesn't play as significant of a role, but in OSPF, the router ID is very significant. In fact, every single OSPF data structure includes the router ID. But we'll go ahead and set it here. They want to set the router ID to 2.2.2.2. It does not have to be a valid address. It just has to be in a 32-bit dotted decimal format. So you could set the router ID to like 0.0.0.1 if you wanted to. Okay? Obviously 0.0.0.1 is not a valid address, but all right. Now if I do show IP protocols now, I can see that my router ID is 2.2.2.2. Okay. So I guess that's okay. In OSPF, we'll talk more about what the purpose of the router ID is in the data structures, but in EIGRP, we don't really see it too much. So now they want us to just verify our configuration of EIGRP. Do show run pipe section. Well, I'll just do router. You can do EIGRP as well if you want. But we don't really have... there's my v4 configuration. Yours might look different. I use different network statements. Yours might look a little bit different. All right. Any questions so far? I told you guys after our Ether channel discussion yesterday that we were going to get into the heavy lifting. Wait till we get to OSPF. That's some seriously heavy-duty lifting. Something on my finger here. It's... All right. Next step. And again, this is, well, that doesn't match what they configured. Oh, sorry. They want us to go into BR2. So I didn't look at the text there. They want us to go into BR2. and investigate BR2. Show run pipe section router. Router EIGRP 10, same autonomous system number. Here, they're basically enabling EIGRP. The way that you can read this, by the way, to identify, let me do a show IP route pipe include C. We have network 4, we have network 5, we have network 6, and we have 255.4. They only have 2 network statements here. A .3 is a block of 4 addresses. A .7 is a block of 8 addresses. A .15 is a block of 16 addresses. A .31 is a block of 32 addresses. So the way you read this is a block of 4 addresses starting at 4. So it includes 4, 5, 6, and 7. Does that make sense? Which includes 4, 5, and 6. It's just bitwise masking. You know, ones we care, or sorry, zeros we care, ones we don't care. But again, how you decide to do the network statement is entirely up to you, as long as it includes whatever interfaces you want to run the protocol on. All right. And they set the router ID. That's interesting that they used EIGRP router ID. That doesn't seem right, but because when we implemented that, I mean, yeah, I guess that makes sense. I was going to see the configuration here. See, we just put in router ID. So I guess either command works, but it adds the EIGRP in front of it for some reason. I actually never noticed that. I've always just used the router ID command. Interesting. Huh. So it's a hidden command. It took it, right? Because I just did router ID. Takes the command, but it doesn't show that as an option. Interesting. I've been teaching this stuff for 20 years, and I just realized that. So, guess you kind of learn stuff. All right. So, actually, technically, the command is EIGRP router ID, but router ID works. Okay. Let's see here. Here they're just describing that what I described, that third octet, a .3 matches 4 networks, which is network 4, 5, 6, and 7. You can enable EIGRP on all the interfaces just by simply doing that network statement. I would never recommend that, because that means that every time a new interface is added, it automatically starts running EIGRP, which we don't want, we don't want to happen. All right. All right. Let's check in with our live stream and see. Yeah. Not a lot of viewers, but oh, we do have some. Yes, I am. All right. Sorry, I didn't see the chat window there, guys. Kind of busy talking. All right, our next task. Enable IPv6 EIGRP using classic mode on BR2. So we go into global configuration mode on BR2, and we execute the command IPv6 unicast routing. We saw that before. I talked about that yesterday. That command is what enables the protocol stack on the router. All right. It's not specific to EIGRP. It's if you're doing any kind of IPv6 routing, you need to do that. The command for IPv4 is IP routing, but that's enabled by default on routers because they're routers. All right. They want us to go into autonomous system number 20, and they want us to set the router ID. So this is interesting. We're using kind of the same syntax here, right? So instead of saying router EIGRP 10, we're saying IPv6 router EIGRP 20, and we're setting the router ID. But guess what's not an option? Network statements. We do not use network statements for IPv6. In EIGRP and OSPF, no network statements. We enable the protocol on the interface directly. Okay, just to summarize a couple things here. Configuring IPv6 EIGRP using classic mode, 2 steps, IPv6 router EIGRP command, setting the router ID. Again, not required because the router would select its own router ID. All right, based on that selection process. But ideally, as a best practice, you want to set the router ID manually. That way you can control that process. Step 3, configure IPv6 EIGRP under the interface. Now, what I would like to do is I don't want to have to go back and look at my diagram. So I'm going to do a show IP route pipe include C just to see which interfaces are actually on this router because it doesn't match in the book. So I'm going to do an interface range loopback 0-2, comma, Ethernet 1/0. Work smart, not hard, because we're implementing the same command on every interface. Essentially, we're enabling EIGRP on all of those interfaces. Might as well do them all at once. Okay, we see our adjacency come up. Unfortunately, as much as I would love to do it, we don't have time to talk about, link local addresses and how link local addresses are used to form adjacencies and what is a link local address. But okay, let me know if you guys need more time to catch up on your configs. I'll put it back up on the screen here. These are the 2 commands that I executed on BR2. All right. All right. So, big difference between V4 and V6. We enable the protocol on the interface directly in V6. We do not use network statements. Okay? All right. We'll try to we got about 45 minutes before lunch. I'm going to try and get through this discovery, and then we'll wrap up and take our lunch break. But all right, any questions so far? I'm trying to be as descriptive as possible, but if you guys have questions, let me know. Task 3, configure IPv4 and IPv6 using named mode on the distribution router. All right, on the distribution, we're going to go into global configuration, and we're going to create the V6 named process. Excuse me, not V6, the EIGRP named process. And that name is going to be Cisco. This name is locally significant to the router. The name does not define the autonomous system. It is just a locally significant name to identify the named process locally on the router. So we're going to do this on our distribution router. Config T. Named mode Cisco. Notice that we're in config router. If I do a show IP protocols, I don't show the protocol running yet because we haven't created the autonomous systems. All we've done is kind of gone into this named configuration mode. All right. We have to enable the protocol by creating the ASs. At this point, the routing protocol is not enabled yet. You have to define at least one address family. So we're going to start our v4 EIGRP process using AS10. The AS means the same thing in this case. Still has to match on all the routers. AS10. And now if I do a show IP protocols, I should see that I am running EIGRP for process or autonomous system 10. We can also see that it's named mode for two reasons. Number one, there's a K6. K6 only exists in named mode. And number two, we see the name, Cisco, and we see the AS for AF for IPv4. Also, we see the metric version is 64 bits. We'll talk about what the rib scale metric is in a little bit. That's a very important concept. The router ID was selected based on the loopback. All this other stuff is the same as it would be in classic mode. All right. This command enables the address family to start the protocol for the AS. It puts you into address family configuration mode. You can actually see that. Config-router-AF. Let's see. In the IPv4 address family, you can enable EIGRP for specific interfaces using the network command and define other general parameters. So if I do a question mark here, you can see what my options are. AF interface. I can set metric parameters. I can establish a static neighbor. I can put my network statements. I can shut down EIGRP. That's not something that's available in classic mode. And actually, in older versions of iOS, you would actually have to do a no shutdown because by default, it is shut down, even though you implemented it. So you might have to do a no shutdown to turn on the EIGRP process. Okay. Here they want us to set the router ID, and they want us to enable EIGRP the lazy way, which is basically just turn it on every interface. Again, these apply to the entire EIGRP process, don't they? These concepts. So we're not under topology base. We're not under AF interface because the router ID applies to the whole router. But notice the syntax is the same. It didn't change. Network statement syntax is the same. That didn't change. We see our adjacencies come up. We have two adjacencies, which makes sense based on our topology. Okay. You can enable IPv4 EIGRP interfaces in named mode with the network statement, just like in classic mode. They can be more specific. They can be more generic. We use the most generic one, which is not recommended at all because, again, now any interface, any v4 interface I add to this router is now going to be part of EIGRP. I think in this case they're just doing it because there's a lot of steps in this lab, and Notice that we obtained two neighbor adjacencies between HQ and dist. All right. The next thing they want us to do is to go ahead and start the process for IPv6. Now, we're already in router configuration mode. In fact, we're in address family subconfiguration mode. You don't actually have to get out of that mode to go into address family for IPv6. If I go into address family for IPv6, it automatically takes me there. Also, notice what happened immediately. I established adjacencies. That's really important to understand, because in classic mode IPv6, we had to go to the interface and enable the protocol directly on the interface. In named mode, it automatically turns it on all of the interfaces. That can be an issue. We need to be aware of that. So you may have to configure some passive interface options before you enable it. Well, actually, that's not possible, because you have to go into the address family to be able to enable passive interface. Just be aware. It automatically enables IPv6 for EIGRP on all the interfaces in named mode. We got to set the router ID. We don't have to, but it's recommended. Distribution router is router 4. Again, that router ID needs to be unique throughout the entire autonomous system. Let's see. When defining the IPv6 address family, it is you have to use the right AS number. All 4 routers are using AS20. Remember, the AS has to match in order for us to be able to form an adjacency. Notice that the IPv6 EIGRP neighbor relationship is established as soon as you enter the address family. EIGRP for IPv6 in named mode does not need to be enabled on the interfaces. It's enabled automatically. To prevent an interface, you have to shut it down under AF interface. So I could essentially say like AF interface default, and I could say shut down, and that shuts down EIGRP on all my interfaces. I could say no shutdown. I could go into, let's say, serial 20, AF interface, serial 20, shutdown. That shuts down EIGRP on the serial 20 interface. You could use passive interface, but passive interface is kind of weird. It doesn't technically turn off the protocol on the interface. It just stops sending hellos and accepting hellos, which means you can't really form an adjacency, but the interface is still part of the topology table. In this case, the interface wouldn't even be part of the topology table. I'm going to do a no shut though, because I don't want to break my lab here. All right. IPv6 address family configuration will display the running config as a unicast address family. Note this is a normal for neighbor adjacencies to reset after putting in the router ID. So we've done our configuration. Now what they want us to do is to go through and do our verification, which means that we're now going to learn what some of the verification commands are. Okay. And if you think about the data structures, if we logically walk through the steps, the first thing we want to do is look at our neighbors. So they want us to run the show IP EIGRP neighbors command on HQ. And I will break down what this output shows us. And by the way, we also have show IPv6 neighbors EIGRP. I'm going to run them and kind of look at them together. There, we got them on one page now. So if you look at the data, and by the way, in most of these protocols, Simply replacing the word IP with IPv6 does the same thing in IPv6. So looking at the IPv4 neighbor table, H stands for host index. That's essentially the order that the neighbors came up in. So this neighbor was first, this neighbor was second, this neighbor was third, this neighbor was fourth. Address is the next hop. That is the IP address, the physical IP address on the neighbor's interface that they use to attach to me. So in essence, this becomes the next hop in my routing table for prefixes that I'm routing to those destinations. Interface. The interface I go out of to get to that next hop. So this is my local interface. So the 255.6 neighbor is on my Ethernet 1.2 interface. Hold time. How long I'm going to maintain that adjacency if I don't receive hellos. Remember, it's 5 and 15 seconds by default. So really, this should never go below 10. If it goes below 10, you missed a hello. If it goes to 0, you delete the neighbor. Uptime, how long the neighbor's been active. And then these values on the right, smooth round trip time, retransmission timeout, queue count, sequence number. We obviously know what the sequence number is. Sequence number allows us to track the sequence timestamps that we have on, or not timestamps, but the sequence references that we have in our packet headers. Smooth round trip time, retransmission timeout. These are values that are used to determine, it's part of the RTP process. We use these values to determine how quickly I should expect to receive an acknowledgement. And if I don't receive an acknowledgement within that window, I can assume that the packet was lost and I'll retransmit it. We don't need to understand, specifically what the numbers mean or how they're calculated, but that's what they represent. It's part of the reliability mechanism of EIGRP. Notice the V6 output is formatted exactly the same. The only difference is timers are slightly different from a measured standpoint. And instead of using, the global IP addresses on the interface, we use link local. Link local addresses are used in IPv6 for everything. Every single V6 interface on your phone, on your computer, on a router has link local. Link local addresses always exist. So they're used to form adjacencies. They're used to exchange information because they always exist. All right? I would love to say more about them, but we just don't have time. I got to keep moving forward here. All right? So, you know what's nice about this and why I decided to show you the V6 output? You don't have to relearn everything if you go to IPv6. Everything is the same. The algorithm is the same. The metric is the same. Everything is the same. Okay? I think I mentioned earlier that the K6 value is used for IPv6. I mistakenly said that. It's used for named mode. But the metric is identical for IPv4 and IPv6 in either mode, classic or named. All right? The next thing they want us to run is the show IP EIGRP neighbor detail command. We see a little bit more information here. Like, for example, the software version, how many retransmissions, retries. That's important. If that number is incrementing, that indicates that there's either congestion with that neighbor or there's delivery issues with delivering the packets to the neighbor. Prefixes. How many routes I'm learning from the neighbor. How many routes I'm learning from the neighbor. I'm learning 9 routes from 255.14. I'm learning 4 routes from 255.10. I'm learning 2 routes from 255.2. And I'm learning 3 routes from 255.6. Watch this. Show IP route pipe include 255.14. That's weird. Ah. Okay. 25514. Oh, it's because of my past selection. That's a serial one. Let's do the 255.2. We have two prefixes, and sure enough, there they are. The reason the other one didn't show anything is because it's in the topology table, but it didn't go in the routing table because the metric was higher. So I'm learning about 9 prefixes. Where'd it go? I'm learning about 9 prefixes from 25514, but I don't have 9 prefixes in here from 25514 because they're used here. If I do a show IP EIGRP topology, I don't know if this will work. I'll give it a try. 255.14. Yeah, it didn't work. I should see those 9 prefixes here. There's 1, there's 2. Why aren't there 9? Let's see. 1 prefix, 2 prefixes. Huh. Doesn't match up. Anyway. 9 prefixes. I'm trying to think of where the additional prefixes would come from. If I look at, which router am I on? I'm on HQ. 25514 is this other serial interface. That is curious why they're mentioning 9. One, two, three. Huh. Because that's this serial link here, this 1.5 meg link. That's another issue. If I do a show IP route, we're using serial 20, which is 255.10. That doesn't match up with our network here because... Oh, no, that makes sense. That makes sense. 1.5 is slower than 2, which means it has a higher cost. So we're learning the routes over this serial link. That 9 is throwing me off, though. I'm trying to figure out why it's showing 9 prefixes. Let me see if I can show IP EIGRP neighbor. Yeah, I didn't know if I could do that or not. Serial 20 and serial 21. Yeah, I'm just trying to figure out if I can see. I thought the topology table would show me that. And I don't see any option to kind of drill down into those prefixes. This is just bothering me. I mean, obviously I've seen this many times every time I teach this class. But when something doesn't kind of match up, it gets my thought process going, and then I get stuck in a rabbit hole. It just doesn't make sense that we would be seeing a 9 there. I'm not saying it's wrong. I'm just trying to figure out why it's a 9. So if we look at 255.2 in our topology, that's this network. I don't think all these loopbacks are running EIGRP. 4, 5, and 6 it makes sense here. We see the prefixes. And then for 255.6, 3 prefixes. And we see the 3 prefixes. That 9 is just bugging the crap out of me. Anyway, we'll move on. Yeah. We'll move on. We have to. Just wish I could. Where do you get these labs? Can you get them for CML? I built these labs. All right. All right. I'm going to go back later and figure out what the 9 is, why it's showing a 9. I'm not saying it's wrong. It just doesn't make sense to me. Okay. So here they're kind of breaking down the columns that we already broke down: H, host index, address, interface, hold time, smooth round trip time, the amount of time in milliseconds required for the router to send the packet to its neighbor and receive an acknowledgement. So that's based on the delay. You know, we kind of measure the average response times, and so that's a number that's not static. It's going to constantly change. But the whole point of measuring that is to say, okay, if I don't get an acknowledgement within a specific time frame, then I expect that the packet is lost and I'll have to retransmit it. And then the RTO is the amount of time the router is going to wait before it actually sends that retransmission. Queue count, we want that to be typically 0. Queue count means how many packets are in the software queue for that particular peer. If it becomes greater than 0, that indicates that there's some sort of network congestion. Okay? Step 6 we already did. We verified the V6 neighbors. We don't have to redescribe the table because it's formatted the same way the V4 table is formatted. All right? Other than the fact that we're using link local addresses. Another command that we can use to verify the operation of EIGRP is the show IP EIGRP interface command. Show IP EIGRP interface. Essentially, this command tells me which interfaces are running the protocol. E11, E12, serial 20, serial 21. Formatting is a little messed up here. Let me just change the size real quick. And rerun the command. I'll put it back up to the larger size, but I wanted to make sure the table is formatted correctly. How many peers do I have on that neighbor? And by the way, the neighbor relationships are physical, directly connected. I will never form a neighbor relationship with a router that's 2 hops away. And, you know, smooth round trip time, pacing times. We don't really care about all those timers. Transmit, queue, you know, these generally will always want to be 0. If these numbers are not 0, that means packets are being delayed. Pacing time for unreliable versus reliable, don't care about that. Multi-class flow timer, we don't care about that. So really the only usefulness of this command, in my opinion, unless you're doing some serious troubleshooting, the only usefulness of this command is to identify which interfaces are running the protocol and to see how many peers you have on that interface. It should match up with what you expect. Okay? It should match up with what you expect. Oops, I just closed all my terminals. All right. That's okay. We'll just go back in. All right. Okay, come on. Let me go back. All right. Interface column, peers column. We talked about that. Another command that we can use to verify the operation of EIGRP, and by the way, you have these in IPv6 as well. Another command is show IP EIGRP interface detail. Now, this command is useful because for a couple of reasons. First of all, it shows us in consecutive order which interfaces are running EIGRP. So this Ethernet interface, this Ethernet interface, this serial interface, this serial interface. But look what else it shows us. It shows us the timers, hello and hold time, the default timers. Notice on the serial interface, we have the same timers. Okay. There are different timers for slow speed links, links that are slower than 768K. I think it's 30 and 90, but don't quote me on that. All right. Again, same information. We just get this detail. The other thing we see here is authentication. If it's enabled on the interface, how many hellos were sent, how many hellos were expedited, is split horizon enabled or not enabled. Split horizon is a rule that says never advertise a route back out the same interface that you received it on. That's enabled by default with distance vector routing protocols. There are specific scenarios where you might want to disable that. Step 8, show IP protocols. We've run this command a couple of times, but we didn't really break down the components of it. So let's go into branch 1 and run the command show IP protocols. Okay. This is not specific to EIGRP. This will show me RIP. It will show me OSPF. It will show me pretty much everything. This is the autonomous system number. If I'm applying any kind of filtering to the EIGRP process, we'll see that later on. What is the autonomous system number? What are the K values? Again, we know we're running classic mode in this case because we don't see a K6. Don't care about that. Router ID. This is the administrative distance for EIGRP. Do you guys remember what administrative distance is used for? So, say that one more time. No, it is not. No. In a router, we have something called the route selection process. Okay. If I am learning about the exact same route within the protocol, so like EIGRP as an example, I will choose the route with the lowest metric. So if I've got an EIGRP route for 10.10.10.0/24 and it has a metric of 22222 and the next hop is 1.1.1.1, and I learn about the same route. Now, in this case, this would never happen, but I just want to put it visually on the screen so you can see it. 90.1111 via 1.1.1 or 2.2.2.2. It's the exact same route, but I'm learning it from two different sources. I choose the route with the lowest metric. The reason I say this is that this is what you would see in the topology table. You would never see this in the routing table because we only put in the routing table the routes we're using. That's one of the tiebreakers. If I am learning about similar prefixes that match a packet, I will route using the best match, which is the longest prefix length that matches. Here's the example. Routing packet 10.10.10.11. That's my destination. And I have a rip route of 10.10.0.0/16 that points to next hop A. And I have an EIGRP route of 10.10.10.0/24 that points to B. And I have an OSPF route of 10.10.10.0/26 that points to C. And I have a static default candidate 0.0.0.0 that points to D. This packet actually matches every single one of those routes. Does the packet start with 1010? Yes. This is what we're matching against, the prefix length. Does the packet start with 101010? Yes. Does the packet start with 1010.0? It does. That's the network ID. /26 is a block of 64, which includes 0 to 63. 11 falls within that block. So the packet matches this route. Does the packet match the default route? Yes, because everything matches the default route. But I would route with this packet or this route first because more bits match. Then I would route with this route second. And then I would route with this route third. And then I would route with this route fourth. Does that make sense? That's called longest match routing. Now, if I change this to, say, 66, then this is no match because 66 falls out of the range. That route wouldn't be used. So then this one would become the first, this would be the second, this would be the third. All right. I'll fix that. The final tiebreaker in our route selection process, if I learn about the exact same prefix from different sources, static, EIGRP, OSPF, etc., I will use the route from the source with the lowest administrative distance. So if I learn about a RIP route 10.10.10.0/24 and I learn about an EIGRP route 10.10.10.0/24 and I learn about, or I configure a static route 10.10.10.0/24, or I learn about a I won't use BGP, OSPF 10.10.10.0/24. Connected routes have an administrative distance of 0. Static routes have an administrative distance of 1. External BGP, administrative distance of 20. Internal EIGRP, administrative distance of 90. OSPF, administrative distance of 110. ISIS, administrative distance of 115. RIP, administrative distance of 120. External BGP, administrative distance of 200. And not usable, administrative distance of 255. There's other ones in there, but I'm just giving you the most common. Which one do you think is better? Lower or higher? From a trustworthiness standpoint, which one's better, lower or higher? Lower. So this guy's got an administrative distance of 120. This guy is 90. I forgot one. External EIGRP is 170. Sorry. This guy has an administrative distance of 1, and this guy is 110. I would choose the static route. And remember, we're talking about the exact match. If this was 25, that's not an exact match, and this route would go in and that route would go in to the routing table. We're talking about exact match. Okay? So, administrative distance, you know, that's what we're talking about. And if you look at the routing table, by the way, that's what these numbers represent, 90 and 170. But if you do a show IP route, in the brackets, you will see those values. 90 is the administrative distance. This is the metric. The second number in the brackets is the metric for the route. The first number in the brackets is the administrative distance. All right. All right. Well, we are going to have to pause here because we need to eat. Okay. So for those that are actually watching the live stream right now, we're going to end this live stream, but we're going to start a new live stream in 1.5 hours. So whatever your time zone is, wherever you're from, put it in the chat window if you want. I'm kind of curious to see where people are joining from. Come back in 1.5 hours, and we will continue this discussion. Okay? All right. So I don't want to just keep streaming it, so I'm just going to end the stream. We will start back up in 1.5 hours. Oops. We are going to lunch. All right. So, end the stream.